All right. In this next lecture, this is lecture 11, we are going to be talking about counter application. Essentially, we are going to look at how we can take some standard chips and use them as a counter. So we are going to try to apply it, not design it. So we'll go through counter application and then we'll talk about counter design. So the specific chip that we will be looking at over here is the 74X163, which is a free running 4-bit counter. And we'll also look at 74X169, which is also a 4-bit up and down counter. So it can go up and down in terms of count. So we'll take a look at these two chips in a lot of detail in this particular lecture. Now, in order to save time, I have kind of written down the characteristic of each of the pins, and we'll go through them. So 74X163 chip is a 4-bit counter. It is going to be counting, and now it is going to be counting from 0 all the way to 15, 0, 0, 0, 0 all the way to 1, 1, 1, 1. This is exactly the same chip that your Studio 6 is based off of. So this would be a great time for you guys to sort of capture all the ideas for Studio 6 to become a very, very simple exercise. This is the 4-bit counter. When is it counting? It increments in count. It only increments. This guy doesn't go down. This guy only goes up. It increments in count whenever there is a positive edge on the clock. So that's your first input. Clock. It is a positive edge triggered counter. The second one is clear. It's an active low clear, but this is synchronous. So this guy has to wait for the clock to have a positive edge. Until that positive edge happens, it is not going to be clearing the counter, making 4 of these guys go to 0. There is a load input. Pin number 9, load input, another active low input. It is synchronous, so you can only do this with respect to the positive edge of the clock. And it is used to load an arbitrary counter value. Suppose you wanted to load a particular value into the counter. Maybe you do not want to start at 0. Maybe you want to start at 1. Maybe you want to start at 3. You can load parallelly something arbitrary into the counter. So it's parallel load. Yeah, that's right. It is exactly that. The load input is sort of a control to do a parallel load into the counter. Where are you going to have to give the inputs to be loaded? A, B, C, D, right? So A, B, C, D are your 4-bit input. This is used when the user wants to load arbitrary inputs into the counter. If you wanted to start things at 0, clear it. If you want to start things at a non-zero value, maybe you want to do a parallel load while providing inputs as your starter at the ABCD pins. Next, you have two enables, enable P and enable T. These are sort of used for cascading multiple 74X13 chips. And there is also a slight difference between the two in that one of the outputs, which is the ripple carry output, becomes active. And for that to be active, the ENT enable has to be asserted, has to be 1. But these are two enables that have to be active. They are both active high enables, and they have to be connected to a high input for this guy to count. We talked about the number 5 here, which is the 4-bit input. These are the 4-bit input. That's where you provide your inputs to be loaded into the counter. Well, for that, you would have to use the load input and also have to wait for the positive edge of the clock. QA, QB, QC, QD are essentially the value of the counter, right? Those are your 4 active high outputs, which tell you the value of the counter. QA is your least significant bit of the counter, and QD is the most significant bit of the counter. RCO is a pretty interesting output that we have available to us. RCO, which stands for ripple carry output. It is very helpful in terms of cascading multiple 74x163 chips. Maybe you want to design a 8-bit counter with this. You can do that by using two of these chips. But for that to work, you would also need to use the RCO output. It's an active high output. So what is the use of this? Well, the use is when your counter becomes 15, right? 1, 1, 1, 1. At that time, RCO becomes active. But for this to work, ENT at that time also needs to be active. So as it is going from 0, 0, 0, 0, 1, 2, 3, all of those counts, RCO is 0. When this guy becomes 1, 1, 1, 1, this guy becomes a 1 at that time. All right, questions about sort of the inputs and outputs and their basic explanation. Now let me ask you guys white paper. So suppose you're free running 74x16163 goes from what? 0, 1, 2, all the way to 15, and it'll go back to 0, back to 1, and then it'll go and it'll keep doing that. Do both enable P and enable T have to be enabled for it to count at all? Absolutely right. Both of them have to be enabled. But for RCO to be active, E and P at that time can be inactive. But for it to move from one counter value to another, both enables have to be active. Okay, right. So this is your free running 74x163 behavior, right? For the outputs, right? For the outputs, QA, maybe I should not write QA, QD, QB, QC, QB, and QA. It's going 0 and 1 and 2 and so on up to 15. And it is going to be doing that after the positive edge of the clock, after the positive edge of the clock, and so on. Now, what are some of the things that you might want to do as a person who wants to use this counter? This guy starts at 0, ends at 15. What would you want to change about this? One option is don't start at 0, start at something else, right? So 0 to 15, okay, that's one thing that you might want to do. Or you might say, all right, start at something like 3. So 3 to 15. Or you might say 0 to 9. Start at 0 but end at 9. Or you might say 3 to 9. You guys see that? So you can start and stop the counter at any arbitrary value. Now I can only think of these 4 possibilities. The first one being free running. It keeps doing that anyway. I don't have to play with any of the load or clear inputs. I could start at something other than 0. I could stop at something other than 15. And I could start and stop at a value other than 0 or 15 respectively. You guys see that? So these are sort of the 4 possibilities that you can have for this 74x163 chip. One such problem is being asked on the Studio 6. Now let us talk about the counter operation, and this should be sort of pretty quick. This is the same 163 chip over here. All we have done is we have connected the active low clear to high. We are not clearing it. We are not loading anything into it. We have always enabled it. by connecting both the enables to high. So it is enabled. We are never loading anything into the counter. We are never clearing it. What is going to happen? What is going to happen if you kind of kick things on? If suppose you have this 163 chip, you have powered it up, you have grounded the pin, you have connected things the way they are shown, and you have connected it to a clock, and your clock is running. What is going to happen in terms of the outputs? QA, QB, QC, QD. What is going to happen? All right, let me ask you simpler questions. Is it going to be counting up or not? Is it going to be counting up or not? Yes, so it is going to be counting up. Okay, so if it is going to be counting up, what do you think the first value is going to be? How do you know that? We have never cleared it. How do you know it's the first value is 0? The reality is that there will be a we don't know. That's right. The reality is that it is going to power up in a random state. It could start at 1 or 14 or 9. We don't know. It is just going to arbitrarily power up in one of the states. However, from then on, it is going to be a free running divide by 16 counter. Divide by 16 counter essentially means that you have 16 different states for the outputs. This guy essentially means that this is a divide by 16. Divide by 16 or modulo 16 counter or mod 16 counter. It has 16 different states, 0 all the way to 15. 0, 0, 0, 0 in binary to 1, 1, 1, 1 in binary. And for that to happen, we need to not clear it, not load anything into it, enabled. That's it. And we would get a free running counter. Now, one of the things that a lot of you might struggle with is this. When you are building this on a proto board, when you are actually designing this using hardware, this reality could be okay, right? The random power up state probably is fine. How about simulation? Can we pull this off in simulation? What do you think I need to do in terms of simulation? If it is a real chip, then it randomly powers in one of the states and then it keeps counting. But if it were a simulation, Bennett, you're absolutely right. You got to clear it first. So you have to clear it first. Clear it first. How am I going to clear it? Clear low. That's right. So what you can do is you can put a switch that drives the clear input, and that switch can be used to connect to low and high, right? So when you can activate the switch or inactivate the switch, so you can control the clear. So when you clear, all the outputs will go to 0, and then do the not clear, right? So then you don't clear, and then you can keep running it. So that is something that you guys have to be careful of while doing the Studio 6, because you will run into this issue. If you don't initialize it, then the simulation doesn't know where to start. So it's not going to give you anything at the output. It's just going to show you X, and you're not going to know why. This is the reason why. You need to clear it. You need to initialize it. So clear it, clear first. Then you can make clear, inactive, and count. All right. So I hope you guys will remember this while you doing Studio 6. Let's run through the other items here. Our counter is going to work only when both the enables are asserted or both enables are high. The load input is going to override the counting, which means that as this guy is counting up, whenever you want to load something, by making this load input active, it is going to override the counting. You can load things anytime into the counter. They're all synchronous, but it is going to override counting. Similarly, clear input is going to override the loading as well as the counting operations. All the operations are taking place on the rising edge of the clock because it's a positive edge trigger design. And the RCO output is asserted when the counter gives out 15, 1111. But for this to happen, your ENT should also be asserted. One of the enable signals should also be asserted. All right, so this is sort of like what this is the first one, right? 0 to 15 case. You can do the 0 to 15 modulo 16 or divide by 16 counter. You can do this. And this is sort of the timing diagram because of that. This is your clock. QA, your least significant output, is half the frequency of the clock. QB is 1/4 the frequency of the clock. QC is 1/8 the frequency of the clock. Q16 is divide by 16 frequency of the clock. And then RCO is 1 only when QD, all of them are 1. At all the other times, RCO is 0. So you're essentially counting 0 all the way to 15 and then back again to 0. Also called as the divide by 16 or mod 16 or modulo 16 counter. A quick question. If there was a hypothetical counter that counts from 1 to 17, what would you call it? 1 to 16. Let's do 1 to 16. Right now it's doing 0 to 15, right? So this is 0 to 15. We are calling it a divide by 16 counter or module. 1 to 16. No. 1 to 16 has how many states? 16 states. So it's still mod 16 counter. So the mod blank, right? The number is defined by the number of states the counter has. If you have 1 to 16, that's 16 different states. It is going to be a mod 16 counter. So they are both mod 16, but in this guy is going 0 to 15, this guy is doing 1 to 16. Now, let's do the second option here, which is start with 5, stop at 15, right? So this is start at 5, stop at 15. How are we doing that? Well, the moment you get 15, right? The moment you get 15, load 5 into the counter. Done, right? So that's your strategy here. Load 5 into the counter when count reaches 15. And how do you know count reaches 15? Well, that's our RCO output. RCO output becomes a 1. You flip that by using an inverter, it becomes a 0. And that's an active low input to our load. So the moment you have 1111 over here, this guy becomes a 1, that guy becomes a 0, and you have essentially activated load, which overrides counting. And because of that, whatever you have connected at the input here is going to get loaded into the counter. What have you connected over there? Let's see. B is 0. B is 0, D is 0, this guy is 1, this guy is 1. What is that? 0, 1, 0, 1, 5. You have loaded 5 into the counter the moment count reaches 15. You guys see that? So this is going to go 5 to 15, back to 5 to 15, back to 5 to 15, and so on. Does it do that all the time, even in the first cycle? What is it going to do in the first cycle? Come on, this should be easy. In the first cycle, it could have started at 0. It could have started at 1, 2, 3, 4, 5. It could have started at any random power-up state. However, after the first 15, random state, that's right. The first cycle is kind of random. But the first time you reach 15 for the counter, after that, it will be in that loop of 5 to 15, 5 to 15, 5 to 15, and so on. And because 5 to 15 is 11 different states, this is called a modulo 11 counter or divide by 11 counter. Questions about this? We have enabled it. We are not clearing it. We are loading 5 into the counter whenever counter reaches 15. Straightforward. To stop at a different value, could you replace RCO with a combination of, oh yeah, that's right. Bennett, that's you are kind of a little bit ahead, but that's exactly what we are doing. There. Another way to design a modulo 11 counter is start at 0, end at 10, right? So 0 to 10 will also be a modulo 11 counter. So if you want to do this another way, we are not using load over here, we are using clear over here. So whenever you reach 10, you clear your counter and continue counting. So clear counter when count reaches 10. Count reaches 10, which is what? 1, 0, 1, 0. There are 2 ones in this, right? So you see QA is the least significant. 1, 0, 1, 0. So take QD and QB, use a NAND gate to detect 10. So this is being used to detect a 10. Used to detect 10. And the moment 10 is reached, you are clearing the counter. Goes back to 0, right? So you go 0 to 10, 0 to 10, 0 to 10, and so on. But only for the first cycle, what is going to happen? You power up in the random power up state. When you power up in the random power up state, what is going to happen? If it is within the cycle, you will continue to be in the cycle. If it is outside this cycle of 0 to 10, what is going to happen? Say 11, 12, 13, 14. The first instance QD and QB are a 1, you are going to go back to 0. Right? Won't it go to 0 immediately? That's right. Not immediately. Not immediate. If it powers up at 5, it is not going to do that. So if it powers up anywhere between 0 and 10, right, if it is greater than 10, it is going to do that. It is not going to do that immediately. Okay, you can have this as 1, 1, 0, 0, right? That is 12. So only for certain things it is going to do it, not for all. But if you remove the first cycle, it will come back, right? It will come back to the 0 to 10 counter count. So our strategy is you are using clear, which is going to override loading as well as counting, and you are clearing the counter whenever the count reaches 10. And this is kind of important, right? 10 is the first time both QD and QB are going to be a 1. So the moment that happens, you're clearing it. What does the inside of this look like? It has a D flip-flops. let us see what we have in terms of a new challenge here, which is start the counter at 3, stop the counter at 12, right? So 3 to 12. This is going to be very, very similar to your Studio 6, you guys. All you're doing is whenever you detect 12, you will load 3 into the counter. So that's your goal here. Detect 12, load 3 into the counter when 12 is detected. How are you detecting 12? It is 1100. So QD and QC are going into a NAND gate. You're using this NAND gate to detect that 12 and you're connecting that to the load input. So as soon as 12 happens, you're loading 3 into the counter. You see, A is 1, B is 1, C is 0, D is 0, 0, 0, 1, 1. That's 3. So load 3 into the counter whenever it reaches 12. But for the first cycle, when it randomly powers up, it may not be doing that 3 to 12 counter. It may be doing some random power up state, but eventually it will fall into place with 3 to 12. All right, questions about this example? You guys got to be clear. You guys got to be careful about the initialization of the 74X163 for the LogicWorks simulation. Okay, let us see. I can maybe do this, and that's what you're using for detecting 12. I was gonna stop recording here.